I think now it's about time to start. So welcome everybody to this online lecture in our Forum for Consciousness Research. My name is Johan Storm and I'm leading this forum. And it's a great pleasure to introduce today's speaker, Professor Susan CAREY from Harvard and New York University. Susan CAREY is an eminent developmental and cognitive psychologist who has made several fundamental contributions to the theoretical foundation of human cognition. She was the first woman to receive the David Rumelhart Prize in 2009, and in 2020 she also received the Atkinson Prize in Psychological and Cognitive Sciences for a theory of conceptual change, for which she was credited for having revolutionized our understanding of how humans construct an understanding of objects, numbers, living kinds, and the physical world. So thus, she has also revolutionized the study of the origins of cognition, and this is, of course, highly relevant for our forum for consciousness research. So I'm very happy to have you here. So she has also earlier received several, the William James Fellow Award and many other awards and honors, many more that I can mention here. And these are her two books from 1985, The Conceptual Change in Childhood, and The Origin of Concepts from 2009, which also received several awards. She started in 1972 and received a PhD from Harvard Psychology Department. And from 1972 to 1996, she taught at Massachusetts Institute of Technology in the Brain and Cognitive Science Department. And then at New York University in the Psychology Department from 1996 to 2001. And then at Harvard in the Psychology Department from 2001 and to 2023. So in 2023, she retired from teaching and is now a research professor at Harvard and a visiting scholar at New York University in psychology, and also a visiting scholar at the City University of New York Graduate Center in Cognitive Science. So I won't have time to go into the papers, of course. We'll hear more about your work soon. But before I close, I'll say a few words about our Forum for Consciousness Research here in Oslo that many of you may not know about from before. This is a cross-disciplinary forum, and we had several eminent speakers before, including David Chalmers, Stan Dehaene, Giulio Tononi, and many others. And you can find video recordings of many of these lectures on our website. You see in the upper corner here the link. And here we also announce future meetings and also at our Facebook page. So these are some of the earlier lectures, and here are the three last ones from Mark Solms and Björn Merker in September last year, and then in June from Matthew Larkham. These are also posted on our website. And we also then in June had a symposium as part of the European Defense meeting in Oslo at that time about progress in consciousness research. And finally, I'm happy to announce this meeting already next week, next Wednesday at the same time, just a week from now, the online lecture by the eminent philosopher Ned Block. The title is Can Only Meat Machines Be Conscious? This is, I hope we will be able to attend that also. It's also posted on our website. And now it's my pleasure to introduce and to ask Susan to give her lecture, which will last about 50 minutes, and afterwards we'll have plenty of time for questions and discussion. And Susan, if you can now, I'll now stop sharing my screen. If you can please share yours. Mm-hmm. And we are looking very much forward to your talk.
Great, thank you so much. Let me just, all right, share.
Yeah, now I see it fine.
Okay, great. All right. So now let's see how it. Good. So my whole career, I have been trying to understand the unique phenomenon in the world, namely the human enormous conceptual repertoire. No other animal can think thoughts formulated over the 1/2 of a million words lexicalized in English. And as a matter of logic, an account of this has to begin with innate representational primitives, and then learning mechanisms that get you from there to the adult repertoire. That's just a matter of logic. And all the debate concerns the richness of the innate primitives and the learning mechanisms that get you from here to there. In this talk, I assume the computational theory of mind. This is a talk about the origin of mental representations. We cognitive scientists who study mental representations take them dead seriously, dead literally. There are symbols in the mind. And if there are symbols in the mind, then there's a question of what those symbols refer to, the entities in the extension of a symbol, the meaning of the symbol, its content, and the form of the symbol. What is the symbol like? Okay, so this is not a metaphor in cognitive science for those of us who accept the computational theory of mind. As Jerry Fodor's slogan was, no computation without mental representation. Okay, so what's the origin of the adult representational repertoire? In my 2009 book, and also Liz Spelke in her 2023 book, we argue that the innate primitives that humans get off the ground with, and that are shared with other complex animals as well, include abstract conceptual representations. That we start with some conceptual framework concepts that get learning off the ground. And in my book, my examples were the concept of an object, the concept of an agent, causal, intentional, and communicative agency, and the concept of number. And in Spelke's book, she also includes in her system of what she calls core knowledge, representations of objects, agents, number, the same ones that I did. I was drawing on her work and object in my book. And she includes social categories, social relations, and then also the representations needed for navigation and form representations. Now, these representations are cognitive, according to both Spelke and me, because they're abstract, they're amodal, they're not tied to any particular perceptual modality. They play a role in planning, action planning, and inference. They have computational roles. And they're just conceptual on their face: agent, causality, number. Recently, Lawrence and Margolis have written I think, 602-page book on a rationalist account of the origins of concepts. And they summarize at the end of this exhausting tome the concepts in what they call the acquisition base, which is just the innate primitives. Thus, okay, so I'm only going to give you a second to look at that, but that's a lot more than what Liz and I did. But it does include number, right? agency. It includes the ones we do. I think object is on here as well, probably. Yes, objects, right? And the idea is that this list is not exhaustive. So I've added 0 because I'm going to talk about it. It wasn't on their list, but all the other ones that were on their list. But the point is, this is just illustrative, right? All right. Something has gone haywire here, I think. So let's not so fast. Let's stop. Let's step back and look at these claims. So, can't get it to advance. Yes. Okay. I'm going to make a bunch of distinctions here. I want to make 2 distinctions among content. One is between target content, the concepts that are lexicalized by the English words on those lists, and proto-content. And then I'm going to begin with that distinction, and then at the end, I'm going to draw a general distinction between conceptual and perceptual content. And I'm also going to really concentrate on this talk about format. So we need to distinguish between iconic and symbolic formats and ask, what are the format of representations of that content in infancy or non-human animals? But I also want to distinguish between content that is fully implicit, not represented at all. And I will illustrate all of those in 2 case studies. One is a number case study, so that one of the concepts on their list, and the same different case study, which is also highlighted from the Lawrence and Margoli's list. So I'm going to begin by illustrating what I mean by proto-content. And so let's start with the claim that bees have the concept 0. Okay, and this is a science paper in 2019 by Howard Giorfa. Giorfa is one of my absolute heroes in this work. He does just gorgeous work on bee cognition. This article was published in Science. Science and Nature are the premier journals in I keep getting this here, in all of science. And there were just gushing commentaries, including by one mathematician who say, Howard et al. Show that bees have the concept of the empty set. All right. What was their evidence for this? Well, this is a really cool experiment, a very cool experiment. They taught bees they gave bees choices between smaller numbers and larger numbers. Like on the left, there might be 7, and on the right, there might be 3 dots. On the left, there might be 2 dots, and on the right, there might be 5. So, in each case, there was a small number and a big number, and the bee had to choose the smaller of the 2. And the bees learned that very quickly. Then, with no further training, they gave them a choice between nothing, 0, and some number. And without any training, they treated nothing as less than 3 or 5 or 7. Okay. Right. Okay. That's cool. I mean, that shows that they represent nothing, and that it's integrated with representations of number. Right. That's really interesting. But the correct thing to say is that bees have a proto-representation that expresses content that overlaps with the concept 0, namely nothing, right? So nothing, 1 minus 1 is nothing. Karen Wynne had already shown that, and if you want to know how, I can tell you later. And what they add is that they know that nothing is less than something, right? That's interesting. It's the same relation as 3 is less than 5. However, that's not the concept 0. What the concept 0 that got math that only arises, with the development of Arabic notation, involves the proof that 0 times n is 0. 0 times n is 0. That's the concept that enables the base system. That there's no evidence for that in bees. Now there might be, maybe Eurifa could do it. And the empty set, come on, give me a break. That would require the concept of a set. I'm virtually certain that bees do not have a concept of a set. The concept of a set. Okay, so what is a proto-concept? It expresses some of the content of the target representation, but not all. Okay. And the art is discovering when you're attributing content to a non-human animal or to a baby, what aspect of the content of the target representation is represented. Okay. So I think showing that bees and babies have the concept nothing is interesting, but don't call it the concept 0. All right. So now I'm going to look at integer. So integer is the concept number that Lawrence and Margolis attribute to the acquisition base, to non-human animals and babies. And that's because there's tons of evidence that both animals and babies track the cardinal values of sets, right, or of collections. There's 2 systems of representation that do that. One is the analog number system. These are perceptual and visual working memory representations of attended collections of individuals. So the first order content in these representations are the individuals, the disks, the lines, and the second one, the motion ones, you're actually seeing little fragments of motion going in particular directions or at particular speeds. And when you attend these, you can't attend each individual in parallel all at once. And when you remember them, when you place them in working memory, you throw away the information about the individuals. You represent the total area, the total number, the average size, the average orientation, the average direction of motion, the average speed, the variability, and all those things. You make summary representations of all those second order properties, but you don't maintain the representations of the individuals in working memory, and you can't simultaneously attend to all of them at once. And each of that second order content is represented by an analog magnitude system. An analog magnitude system it's a very basic coding scheme in perception. It can represent any dimension of experience that goes from 0 to open-ended, like brightness, loudness, speed, area, number. Okay. And basically, the symbol itself is a quantity. These are analog symbols. That's why it's called the analog magnitude system. And in the system of representation, noise is a linear function of the magnitude of the quantity. That is, these systems exhibit something called scalar variability. The mean estimate of the magnitude and the standard deviation of those estimates, that the ratio between those is constant. That's Weber's law. This means that discriminability is strictly a function of the ratio between the 2 magnitudes that are being represented. That's Weber's law. And Jake Beck, a really good philosopher of perception, shows us how scalar variability establishes that the symbols are analog. That's a really nice paper if you're interested. Okay, so this is how this works. So you have a small collection, and here the function between the number and the symbol is linear, but it could also be logarithmic. And you can see that as the size of the collection gets bigger, the analog magnitude symbol gets bigger. And what you can see here is Weber's law. If you just look at the lines there, and which are the symbols for the number, it's hard to tell which one is bigger, but it's easy to tell 1 from 2 or 2 to 3. That's just the strict ratio, ratio dependence of Weber's law. Okay, so these representations, these analog symbols, have integer content. They are representing the cardinal values of attended collections of individuals, although merely approximately. They support numerical comparison, addition, subtraction, multiplication, division, and ratio calculation. These are the representations by which animals compute probabilities. There is no doubt that there's numerical content, right, in non-linguistic minds. However, these are not integers, okay? Why are they merely proto-integers? Well, they're not exact. They're limited by the resolution of perception. They only go up to like 500. If you get too many of them, it's too dense and it just looks black. It's not based on the successor function or Hume's principle that one-to-one correspondence guarantees numerical equivalence. And it does not generate representations which, together with logical operators and quantifiers, can generate all arithmetic. Okay, so this is a paradigm proto-integer concept. The second system is parallel individuation. This is limited to small sets, and the difference is here the representations of specific individuals are maintained. They can be attended in parallel, and they're held in working memory with the identity and the relations between them in a model maintained. And so the empirical signature of this is that it's not limited by ratios. It's an absolute set size limit or absolute capacity limit. And here's an experiment that shows you just how different that is from the analog magnitude ones. You show an infinite objects that can be put into a box in which they can reach but not see. So you show them a box, you shake it, it's empty. You put 3 objects on the top, then you look at them and you stick it into the box through a slit, and then the child is allowed to put their hand through the slit to get the objects out. And they will reach the objects out, maintaining one-to-one corresponding, stopping when they've gotten the number that went in. And sometimes you do a magic trick and you hold an object out of reach. And the dependent measure is, do they search longer when there should be additional objects in the box than when they've received all the objects they saw go into the box? And they do this task. They love this task. Okay. And here's the finding. This is a different score. 1 versus 2 means how much longer do they reach when 2 have gone in and only 1 has come out, compared to when 1 has gone in and 1 has gone out, and also when 2 has gone in and 2 have gone out. Okay, so you see success here is they're reaching longer when there should be something in the box. And that's true when it's 1 versus 2, 2 versus 3, 1 versus 3. But look at 1 versus 4. They reach exactly the same when 4 have gone in, they've gotten 1 out, as when 1 has gone in and they got 1 out, right? They do not distinguish 4 from 1. Okay, this is the set size signature of parallel individuation. This is not the analog magnitude system. Discriminability is not a function of ratio. They also fail at 4 versus 2. Okay. So what's happening there? They're representing these collections with mental models that maintain a representation of each individual in the collection. They also maintain the spatial relations between them, temporal relations if they're temporal, and they can't represent 4 or 7 or 8. because it exceeds the limit of parallel individuation. So number is represented in these models. It's instantiated in the model, but there's no symbol for number in the model. Okay, that's how parallel individuation works. So the content of these parallel individuation models is also proto-integer. These are exact cardinal values of small collections. They support, those are captured in the model. They support numerical computations, one-to-one correspondence as they're planning a set of reaches. And addition and subtraction as you add or subtract things from the set. But again, this is wildly proto-integer, right? There's a very limited range of cardinal values. There's no summary symbol for any cardinal value to combine with quantifiers, logical operators, and so on to generate a symbolic system of arithmetic. All right. So I've just illustrated what I meant by proto-content. And let me just tell you, every concept on Lawrence and Margoli's list is either mildly proto or wildly proto, like zero or integer is to what's actually in the content in the acquisition base. Okay. Now I'm going to illustrate further. I'm going to illustrate that the reason that the number representations have proto-content is that their format is not symbolic. Okay. So there's long been the appreciation that there's two very, very different kinds of format of external and mental representations. So consider the content of the noun phrase, two dogs lying on the grass. Okay, well, that symbolic representation, namely that phrase, two dogs lying on the grass, expresses that content. So does this picture. Okay, so the picture is an iconic representation of with that content, and the phrase is a symbolic one. But there's a huge literature in philosophy, and in my first version of this talk, I went through, and psychology and cognitive science, several different proposals for how to draw that distinction. But this talk got too long, so I'm just going to give you the one that I find the most elegant, and it actually unifies all of the others that were on that list. If you're all interested in this topic, you must read Gabe Greenberg's Phil review paper called The Iconic Symbolics Spectrum. And what he says, the two systems are distinguished in the nature of the semantic processes through which symbols are assigned content. And there's a two-way interrelated distinction. The two systems differ in the relation between the content, that is what's being represented, the extensions and the meaning, and the symbols. For iconic representation, there's a uniform across the whole system of representation, a uniform lawful function that relates the symbols, the things in the extensions of the symbols to the symbols. Whereas in symbolic systems, there's no such thing, right? You can't go from a representation of a table to what the symbol is that also tells you how to get from a representation of from a perception of a dog to what the symbol dog is. There's no uniform function of that sort. It's just a list in the symbolic ones, an arbitrary list. And the semantic processes that determine the content of the symbol are therefore correspondingly different. So if you've got a symbol in the mind, the rule that specifies what that symbol means, it specifies a function on the symbol that mentions the symbol, whereas in the symbolic system, it does not mention the symbol. So this is Greenberg's way of saying that. For any symbol, then that little square bracket thing says the content of that symbol. For iconics, is the content such that the relation, and that relation is just the inverse of the lawful relation between the things in the world and the symbol. So it's that the inverse of that relation on that symbol gets you the content, right? Whereas in symbolic semantics, there's no such thing. The content of symbol one is just whatever whatever gives you the meaning of the word dog, and then whatever gives you the meaning of, and whatever gives you the meaning of 7, right? Okay. All right. So the ANS and the parallel individuation are paradigmatically iconic on this view, right? So that's what all analog systems, there is a uniform system that makes a symbol be a linear or logarithmic function of the thing that's represented. That's the uniform, lawful, across the whole system function. And so the meaning of those symbols just depends upon the inverse of that. What makes that top symbol be 1 depended upon the unit that I chose for it to be 1. And the second one is 2 because it's twice that, right? Okay, so this is analog number representations are just textbook paradigmatically Greenberg iconic representations. And parallel individuation ones are as well, because they function, it's not the same, right? They function like pictures and maps. So the content of those models are spatial and temporal relations populated with individuals and properties whose locations are specified relative to a central viewpoint. And the natural dependency here is a projection geometry between the thing that's being represented and the model, the map. For a 3D space to be the content of a pictorial representation or a map, the picture or the map must be a symbol that is a uniform projection of that space. Okay. So again, that's gone through in the Phil Review article, and then there's a special one on map semantics, which is a recent paper. It's beautiful. Okay. So here is a parallel individuation model of a table with 3 objects around it. And that you can't make it bigger, right? Because you're limited in these representations to 3 or 4, where you can maintain the symbols. And there's no symbol for number in this, but number is instantiated in the model along with lots of other second order properties. Okay. This is not how language works. Natural languages have first order representations that are words, is a table under all 7 not. There's no uniform progression from what those things mean to what those symbols are. And you can't recover what is means by the inverse of such a thing. And that's also true for second order subpropositional syntactic semantic combinations, morphology, phrasal structure, propositions, combinations of propositions. Each language does these different and arbitrarily, although each language does all those things. Okay, so natural language is first and second order symbolic. It just represents entirely differently than the iconic systems in core cognition. So this has 2 consequences. If this is right, the symbolic representation of integers, like in a count list or Arabic numerals, should be hard to learn. And boy, is that true, right? Over cultural construction, representations of integers don't emerge in the archaeological or in the anthropological literature. Many people are not in numeric cultures. They don't have any representations of cardinal values above 2 or 3. Um, um, and they start with tally systems and only get to count lists after 30,000 years, right? And over ontogenesis, children in a Nubra culture learn the count list. They learn to count before they're two. But they don't learn what one means until about 24 months. And then it takes them 6 months to learn what two means. And then it takes, 3 or 4 months to learn what three means and so on. And they don't figure out what seven means until they're between 3.5 and 4.5. Okay, so it's really hard for them to create symbolic representations of exact cardinal values. And there's a proposal that I don't have time to make an argument for here. I just don't have time in the talk, which is that innate human-specific support for symbolic natural language plays a crucial role in the construction of integer concepts, right? Okay. All right, that's all I'm going to say about number. The point is that the content of number in the acquisition base is proto, and that follows from its iconic format. Now let's go to the second case study from Lawrence and Margolis. Representations of the abstract relations, same and different. I want to illustrate fully implicit content first here, and then I want to show you how, well, let's just start with that. Okay, so here, this is work that I have done. I did a lot of the work on parallel individuation I was just telling you about. But this work is all done in collaboration with Jean-Remy Hoekman, and the most important part of it, I had nothing to do with it all. So his picture is on this all the time to remind you that he's a French psychologist in the CNRS in Lyon. Okay, there's no doubt that the contents, same and different, are attested in non-linguistic thought. And the first demonstrations, and the only ones that's described in the Lawrence and Margoli book, is matched to sample and non-matched to sample. And here I'm going to illustrate with Giorfa. So although Giorfa was on the paper that claims that bees have zero, he also did, as I said, he's absolutely one of my heroes. So it's this very elegant experiment. So the bee walks into a Y maze, and at the beginning there's a sample. There is a red square. And then he walks along the Y maze, and when he gets to the choice, one of the choices has a red square indicating that choice, and the other one has a green square. And the rule in match to sample is if red, choose red, or if green, choose green, right? Choose the same. Now, they can learn that in 12 trials. It's really easy for bees, and so can babies. Babies can learn match to sample in 12 trials, 12 reinforced trials. It's really, really obvious. And in non-match to sample, the rule is equivalent to choose different. If red, choose green, and if green, choose red. Now notice I've just stated that as just two associations between particular colors and what to do. And that could be what the bees had learned, in which case we haven't said anything about same. But what Gierfe et al. Showed was that after those 12 trials with red, where you could have just learned if red, choose green, choose red, and if green, choose green, it generalizes to new color pairs, or with no further training to oriented Gabor patches. So if right facing, choose right facing, if left facing, choose left facing, or to little cotton balls impregnated with odors. If anise, choose anise. If banana, choose banana in match to sample. Okay. So the bees have learned some abstract rule with the content choose same, right? And that is right. They have, and so do babies. In 12 trials, really easy. But how is the content same represented? Is it a symbolic same as in same with two arguments? The rule is choose same, where the symbol same is represented. Is it iconic? If so, how could that possibly work? Or is it fully implicit? And what I'm going to show you next is that in this case, it's fully implicit. The content same is not represented at all. There's no symbolic representation at all of the content same here. Okay, so this is an experiment that Jean-Remy and Shil Modi and I carried out. And then Zantal, who is a wonderful comparative psychologist, did the same experiment with pigeons with exactly the same result. Of course, with the babies, it's not a Y maze, but I'm going to keep illustrating it with this because it's the same structure. So the first question we asked was, well, look, what rule did they learn? In match to sample, did they actually learn the rule choose same? And in non-match to sample, did they actually learn the rule choose different? So we trained them on in the way we did it, we trained them on different pairs on each case from the beginning. They also still learn it in 12 trials. And so then we tested them on new novel pairs. And the way we tested them, in tests, there were two kinds of trials. They saw the sample, and then they saw just one of the choices. So if they have learned choose same in match to sample, they should know what to do in this case, because what they're given is the choice that they should make, right? And this should be harder. If you give them just the other one, they have to make an inference. They have to infer they should go to the other one. And it also requires a representation of not. It's not the same. It's not the same, so choose that. So the prediction is if they actually are representing the choose same rule and match to sample, they should succeed at this, and this should be harder, or they should out and out fail. And what happened is indeed they're following the choose same rule. Sorry. In match to sample, they succeed when the conditions of their rule are available to them, and they fail when it's not. Okay, both pigeons and babies. But how about non-matched sample? Are they following the choose different rules? Okay, well, the choose different rule, it's just the opposite. If they're following choose different, then this one is the one they should seed at, because this is what's contained in the rule, and this one requires inference and not different, right? So you should see just the flip of the other. Okay, so that's what happened in match to sample as expected, but here it's just the opposite, right? So instead of succeeding when the condition of their rule choose the different is what they are seeing there, they utterly fail there, and they succeed again when what they have is same. And what this shows is that the rules they've learned are seek same and avoid same, right? Not seek same in one case and seek different in the other. But that's not the important point to my dialectic here. The important point to my dialectic here is that neither of those rules combines with not. Same does not combine with not, because whether it's seek same or avoid same, if you can compute that this is not the same and infer what you should do on that, you should still know what to do, right? And they utterly fail. Okay, so what is going on here? Why do they fail to do that? To combine same with not and to represent only same. So the proposal is that there's fully implicit content same. Here's what they are actually doing. They learn a little program that goes like this: encode the sample in working memory. So they make a working memory model of this sample. And then the rule is seek sample, seek that, right? And non-match sample, it's avoid that, right? So the representation of sameness is implicit in the match computation that underlies any act of recognition or categorization, right? That's what you do when you recognize something. You have a threshold of matching, and that content is largely what's lexicalized in the content same, right? And abstractness is achieved by absence of a constraint on what representation can be placed in working memory. Okay, so there's no symbol for same. You shouldn't say it's a seek same rule, right? It's a seek sample, store sample, seek sample rule. There's no symbol to combine with not, at least in a rule, not same. Okay. So that's what I mean by fully implicit content. There's no symbol of any kind for the content. The content is realized by the computations that actual mental representations that are being deployed participate in. Okay. All right. So I am running late. Yeah, well,
don't worry too much about that. We are flexible.
well, also I still have 15 more minutes before I'm done with it, so I will go quickly. All right.
Yeah.
So now, however, beyond fully implicit representations, infants also actually represent the content same and different in other paradigms. And I'm going to illustrate two, same, different discrimination and abstract pattern learning. And we're going to ask, well, what's the nature of those representations? Okay, so here's same, different discrimination. Okay, fixate on the fixation point. Okay, encode that. That predicts that. Okay, fixate on, encode that. That predicts that. Okay, very quickly, animals can learn same predicts left. And for animals, after a couple hundred trials of learning, and same predicts left and different predicts right. Okay, you can't do that without some kind of symbol for same, right? So the content of the rules are this: if same looks left, if different looks right, because the individuals differ in each pair, right? So in each pair, it's a different two individuals that are instantiating the relationship, same or different. So they're using sameness and difference as the input to a discriminative rule. Okay. Here's another. This is the Gary Marcus abstract pattern learning. Here's the task. You hear for about 30 seconds. P, la, P. Do, nu, do. Do, nu, do. Re, by, re. Okay, so just these syllables, different every time. And the pattern is ABA. Okay, then on test, you hear novel stimuli that you haven't heard before. May, fi, may, or may, fi, may, fi. And both 6-month-olds and adults, after about 60 seconds of this, generalize the familiarization of the pattern ABA to new ABA ones, and they recover interest if it violates it. Okay. Now these patterns are just patterns of same and different across syllables, right? And now I'm talking about genre me experiments that I had nothing to do with. So he showed that they are in fact representing sameness and difference in the whole pattern. So if you familiarize to PPP, do, 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 ra, 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 you generalize to may, and you dishabituate if anything is different among, the new syllables. So may, fi, fi, may, fi, anything. And similarly, if it's PP, la, then you generalize it to may, fi, and then if it differs by all three being the same or a different pattern of same and different, you recover interest. So you are representing something equivalent to AAA, at least there, or all same in the left one, and AAB in this case. Okay. All right. But how are the contents same and different being represented in same different discrimination or these pattern generalization things? Well, is it symbolic? The first and the last were the same, or the first, all three were the same, or the first and the second were the same, and the third was different. Is it iconic? How would it work? It's not fully implicit because the content same is actually conditioning because the items that are the same are never the same as each other across trials, right? It's the sameness that's been abstracted here. Okay, I'm going to argue that there's good reasons to think it's not symbolic. Okay, and there's lots of reasons for that, but here I'm only going to make one. The representations of same in same different discrimination and pattern abstraction paradigms do not combine with logical operators or quantifiers, just like they didn't in match to sample. Okay, so in same different discrimination, that's the one where I showed you, if same look left, if different look right. Babies learn if same look left. They're trained on both of those. Sometimes the things are the same, sometimes they're different. If they're the same, look left. If they're different, they distinguish it from same because they look randomly, right? So if same, look left, but if not same, they don't know what to do with it. So they distinguish it from same, but they don't learn the rule. It's not the same, so I should look at the other one, right? In pattern learning, Jean Remy, again, this is his work, not mine, showed that the representation of same does not combine with all, and it's a really cool study. Let's see if I can get this to go forward. It's a mystery. Okay, good. So within sequences of two items, P, P, do, do, ra, ra, they generalize to may, or may, fi. And if it's A, B, A, B, A, B, they recover to AA. They similarly do that within an experiment with just three, or an experiment with four. Okay. But what have they learned? Did they learn that these are all the same? Or did they actually learn a representation that instantiates the relation same in a model? Okay, so one of the ways he tested that was to test them on PP, la, 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 do, 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 B, 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 nu, nu. Now, we easily see that in each of those sequences, the syllables are all the same. And if that's what they've learned, then they should generalize that to may, and they should recover to may 5, where they aren't all the same. Okay. And adults, that's what adults do after about 30 seconds of that. And the babies do not distinguish them. So they didn't encode those as all the same. Okay. And similarly, if you exceed the limits of parallel individuation with 5 P's in a row, or 6 P's in a row, or 6 laws, 5 laws or 6 laws, so all of these share a common number, just like the ones they do succeed at when it's 2, 3, and 4. So they've heard P, 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 la, 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 la. Then the question is, do they generalize to may, and dishabituate, recover interest to may 5? Okay, and the answer is adults do, and infants fail to distinguish in both cases. Okay, even though they've really heard a lot of same there. You might think, there's just a lot of same, and here there's one that's different, but they don't notice that. All right. Okay. So I'm going to give you one more bit of evidence that in perception and non-linguistic thought, there's no representation of same that can combine with logical operators and quantifiers, by looking at ensemble representations. So I just told you that ensemble representations, we throw away the individuals, especially in working memory of it, right? And we represent the rough summary properties with analog magnitude representations. But we also have the capacity to look at this ensemble, the 16 items, and just notice that all of those are the same. Now that phrase, all same, is a symbolic representation that throws away all of that information that's maintained in the perceptual representations of ensemble representations, but it is a representation that we can apply to that ensemble. And this one can be represented as not all the same, or all not same, all different. That is, each one is different from each other. Those both contrast with all same, with not and all under different scope relations. Okay, so we easily can distinguish between those this way. So the question is, can animals and young children do that too? Now, come on, this is again. Okay, so here is a task called relational match to sample. And the task is, here's a sample, and you have to decide which of these two is most similar to this one. Which one matches this one? And animals, young children, adults easily learn to match 16 different with 16 different and 16 same, if the sample were 16 same, where in each case, in each card, the icons are unique, right? Except for when there's all the same. So all animals and preschoolers and adults quickly learn to match this with this, and one that's 16 same with this. But what rule have they learned? Have they learned match all same with not all same to not all same? So all same with all same and not all same with all not all same, or different rules, all same versus all not same? Okay. Well, you can tell which they learned by having the samples not only be 16 same and 16 different, but intermediate. Suppose you learned the rule, match all same to all same, and not all same to not all same. Well, then you would match this one. There's just these two choices. You would match this one because they're not all the same with this one, because it's not all the same. And you would match this one with this one, and of course you would match this one with this one. But suppose the rule you abstracted when you were learning that task was match all same to all same and all different to all different, all not same to all not same. Well, now that's not defined for any of these. None of these intermediate ones are all the same or all different. So you would have to do it by the one that's closest. So now you would match all same. You'd match this one with all same because this one's closer to all same than it is to all different. This one, it would be in between, and this one would go with all different. Okay, so this is the categorical pattern. If you're matching 16 to same with 16 to same under the rule all same with all same and not all same with all not same, is you match 16 same to 16 same and all the rest of them with all different. And that's what 30% of adult humans do, and it's what 0% of animals do when they've just been trained on the 16 same and 16 different ones. And the other categorical rule under the different scope relations would show this pattern, and that's what the other, the other percent, the converse of adults do, and no animals do that either. Okay, what do animals do? They match on the base of entropy. They match on the basis of an analog magnitude representation of the amount of variability in those arrays. And they cannot be trained. Dogged training, 60,000 reinforced trials, they never learn to sort categorically. All they do is entropy, okay? And that's also what preschool children do. Okay, so same different in non-linguistic representations is absent. Okay, there's no symbol for the relations of same or different because there's no representation of the individuals that enter into these relations. Okay, in parallel individuation model, same and different is holistically instantiated in iconic second-order relations. There's no symbol for the relations in the model to combine with all or not. So here in this iconic PI model, the model instantiates that these are the same shape, right? But that just falls out of the projection geometry that creates that model. Now, animals can react to things being the same shape, right? That's what same different discrimination shows us, right? But it's not symbolized in that relation does not have its own atomic symbol. That's why it can't combine with all or not. There's nothing to combine with. Not this model could be something with 5 objects or something with different objects or something with the objects in different relations, right? You can't have not same until you've got a symbol for same that's been isolated from these holistic models. So the consequences of this is that symbolic representations in same and different should be hard to learn. And they are just as hard to learn as 7 is. So children hear the word same and different frequently, and all 2-year-olds produce them, and they don't learn them in their relational meaning for another 2 years. Okay, that's because they don't have an atomic symbol in the acquisition base to map those words onto. And the proposal is that innate human-specific support for symbolic natural language plays a crucial role in the symbolic representation of the relation same and different, and I can support that view as well. Okay, so what I've shown you, prelinguistic representations of number, the content is proto, in the way, with respect to integer or 0, in ways that follow from the fact that the prelinguistic representational systems are iconic. And of abstract relations, same and different, the content is often entirely implicit, like in match to sample, and the content that is represented is holistically instantiated and map-like iconic systems of representation, and that's only within PI, parallel individuation. Okay, I believe these generalizations hold for all of the contents on my, Spelke's, and Lawrence and Margoli's lists of abstract content attested in animal and infant minds. Okay. Okay. So I'm going to end with just some quick conclusions. When all three of us, I'm arguing against me, 2009, as well as Spelke and Lawrence and Margoli's. When we say that that there are abstract concepts in the acquisition base, for the claim to be that if we want to use the word concept instead of just there are abstract representations in the acquisition base, then we're contrasting it with something. What are we contrasting it with? And the idea is, with perceptual representations. But then the question is, how do we distinguish between perceptual and conceptual content? So the scientifically supported distinction between iconic and symbolic systems provides a motivated basis for distinguishing conceptual from perceptual representations. And here, if you want to see some long tomes that make this argument, which look at Ned Block's The Border Between Thinking and Seeing, or Tyler Burge's Perception, First Form of Mind. Okay. But for independent empirical reasons, what I'm arguing here is that concepts are atoms of propositions. Conceptual systems have symbolic formats. And iconic systems of representation cannot express propositions. Perceptual systems have iconic formats. If this is right, animals have no concepts, and there are no innate prelinguistic concepts. That's it.